Let's move into physical basis for this macroscale monsoon structure. We'll start with Flohn, who was a German meteorologist who noticed that one of the remarkable results obtained was that valleys of South Tibet at altitudes between 3,500 to 3,700 meter enjoy higher summer temperatures than hill stations in the Himalayas at altitudes of 21 to 2300 meters. So much lower altitudes had much cooler temperatures compared to the Tibetan plateau. At least during the warm season, the surface temperatures are definitely higher than the latitudinal average. So if you look at the same latitude and take the average, the local temperatures in the free troposphere were much higher at similar heights. Furthermore, a large frequency of showers and thunderstorms, often with snowfall and hail, lasting during the whole warm season, i.e. without being limited to the time period of the Indian summer monsoon. Many of you may know that the Himalayas are called the third pole because they have got more glaciers than most other places in other than Greenland and Antarctica. So that is the third pole. Of course, there are various issues in terms of seasonality, warming trends, glacier melts, etc. So what is different about the Asian summer monsoon that corresponds to its macroscale structure that we just looked at in terms of the PV on 370K? So we'll look here in terms of the seasonality of the rainfall for the Australian, African and South Asian sector as well as the American sector. And this box identifies the latitudes of Indian monsoon. So you can see that at the box in the Australian sector, which is averaged over 120 to 140 east, so basically the maritime continent into the western Pacific warm pool, has summer rainfall over here. So this is JJA, boreal summer, and during that time Australian monsoon is not active, so high sea level pressure. There is corresponding low sea level pressure here, but this maximum rainfall is near the equator. And if you look at DJF for the Australian sector, you can see that it does shift to the south, and we had seen Australian monsoon as north of 25 south. So this box has some maximum rain. Look at the African sector, much closer to the equator, a little bit south of the equator, but still much closer to the equator compared to the South Asian sector, which has high rainfall during the boreal summer months further north than pretty much all the other monsoon regions. Okay, American sector has much lower rainfall and of course also closer to the equator, even though it shifts south as you expect in the boreal winter months with the ITCZ. Okay, so the main point is then, why is it that the rain is so deep into the subtropical regions of the equator over South Asia? What is special about it? And you do remember this we saw in chapter 1, where we were looking at the Walker cell circulation at the equator and then zonal circulation at 25 north and a meridional circulation section at 90 degree east, which is cutting through the Bay of Bengal. Okay, so you can see here the distance is shown, but you can obviously see the rising motion or the maritime continent, West Pacific warm pool, divergence above the Pacific Walker cell, the Indian Ocean Walker cell, and the Atlantic sector there. At 25 north, you have strong monsoonal heating, creating a similar structure in the zonal, and we talked about the subsidence and the monsoon desert hypothesis and so on, which give us the desert lows that are amplified. This is again the Pacific and the Atlantic sectors, and along 90 east, if you look on the monsoonal heating region, you have very strong upward motion, and so you have meridional circulation, which is cross-equatorial, going down in the southern hemisphere. Obviously, this we will see in a minute has various time scales, as we already implied, especially the intra-seasonal time scale, where there is, within this seasonal mean, there is a flip-flop between the equatorial region and the subcontinental region. So when the subcontinent is convecting at intra-seasonal timescales during the so-called monsoon active periods, there is a anomalous subsidence over the equatorial region and vice versa, with monsoonal intra-seasonal oscillations propagating from the deep tropics into the Bay of Bengal and over to India. Okay, this is consistent with the various factors we've already seen again in chapter 1, mean sea level pressure and surface winds. So you can see the strong equatorial, the cross-equatorial pressure gradient, strong southwesterly jet, low sea levels associated with the monsoon, rainfall, including the East Asian monsoon. And we know that there is plenty of heating here in the summer as well, but there is not much rain at all. And we will see again, but we had talked about the desert low having this lateral exhaust, which reduces rainfall over here and enhances moisture flux and rainfall over here, which is clearly seen as basically a demise of this ITCZ in this upwelling cold high pressure region, with the lateral exhaust creating a stability as well. And that's our lateral exhaust that we talked about coming out of the Arabian heat low, and we talked about how that process works and how it suppresses convection, creates stability over here, whereas enhancing moisture over here. Even though this is a desert source, it actually seriously affects moisture supply on this side. Okay. Looking at the upper tropospheric humidity that goes with it, temperature that goes with it, you can see this is for DJF. Obviously ITCZ, SPCZ, etc. correspond to this. So this is in the upper atmosphere, 500 to 200 hectopascal. So you have temperatures of minus 20 degrees centigrade and above in the upper troposphere of the tropical band. But compare it to the June, July, August temperature, or the same atmospheric column, and you can see that the cool temperatures over here are the coldest you get at these latitudes and are much colder than here. So this is like 23 minus 23 degrees. This is below minus 21 degrees. Okay, so the deep convection over the region and the heating over the Tibetan Plateau and the convection and the rainfall we had talked about there that lasts throughout the warm season and not just the monsoon season, create this massive cooling in the upper atmosphere over here, which is consistent with the vertical circulation we have learned about, especially the one we saw here, right? This deep convection is going to expand, condense, rain, and create very cold temperatures in the upper atmosphere above the mid-tropospheric heating. Okay, so there is obviously a anomalous humidity signature associated with that in DJF. Negative anomalies, all the humidity loading is in the southern hemisphere with the South Atlantic convergence zone, the South Pacific convergence zone. This is the South Indian convergence zone, SICZ, and this is the SACZ. But in the summer you can see massive loading over Tibetan Plateau and over East Asia, all the way into these high latitudes where you have the rainfall extending during the monsoon season, and of course there are corresponding signatures over Africa and America as well. Okay, so this doesn't explain the physical basis of the large-scale structure, but it gives you a consistency check of what other large-scale features are involved given this extratropical heating, which is the farthest away from the equator compared to other locations. And we will see that compared to the desert heating over the Middle East, for example, or even in Australia, the height of the Tibetan Plateau makes a huge difference. And with the heating, you expect the geopotential signatures. So again, in the Bay of Bengal sector for various months, you can see the rising of the geopotential because of the lifting of the pressure surfaces by the convection and warming in the lower heights and cooling way above. And you can see 200 hectopascal, 500, fairly flat in the along 86 east in the monsoon region, at 160 east in the West Pacific warm pool. Not such a dramatic change in seasonality, and this is 850 hectopascal geopotential. Not much of a signature of the heating, and there is even a reversal of gradient here. This is intersecting the orography here, as we can see, which we also saw in the isentropic surfaces, right? We went into 370K because it is way above the orography. Okay, so that's again at 850 hectopascal at 86 east. So just make sure you get the basic points that the monsoonal heating is way north, and it has associated moisture loading and rainfall. The heat fluxes correspond to that. If you compare Ganga Valley sensible plus latent heat versus the Tibetan Plateau, you can see the seasonality here. The sensible heat is peaking before the monsoon, and as the convection happens, temperatures cool down, sensible heat drops off, and you get massive release of latent heat flux, whereas in the Tibetan Plateau you have quite a different distribution of sensible and latent heats, especially there. Somewhat similar, but the contributions are very different in terms of the processes. Or the Bay of Bengal, of course, you expect sensible to be quite low throughout the year, but you have huge changes in the total that includes short wave and long wave, and you have the dominance by the latent heat flux because this is a heavy convecting region. And there are comparisons with Togakor and North Australia and Sahara, but you can see this out of phase sensible and latent heat a little bit here as well. Not as dramatic as here, but still it is there. And Sahara again is very different because it's desert, doesn't have much of latent heat, but sensible heat dominates. Obviously, dry convection that we talked about before, and how at night time the surface friction is decoupled and you get this nocturnal desert jet, etc. Okay, so these are the consistency checks. I will come back and talk about the profiles comparing the Ganga Basin, which is in the plains, ahead of the Tibetan Plateau towards the equator, and then compare it to the Tibetan Plateau and get into explaining how the elevated heating of the Tibetan Plateau seems to be very unique for creating this rainfall so far north compared to the other similar heat sources in the northern and southern subtropics. Okay.